And so now we're going to do some work with prime and composite numbers. I've got a couple examples up here. First of all, we're going to find the divisors of composite numbers. Okay, so I've got 28 and 72 we're going to work with for just a few minutes. To find all the divisors, you could just try to think about all the pairs of numbers that multiply together to get 28. For instance, 4 times 7, right? 4 times 7 will work. So both 4 and 7 are divisors of 28. 1 and 28, that's the obvious one. But are we missing anything, right? So you always want to think about, is this all of them or am I missing some? And so there's a nice little organized way or technique to ensure that you're not missing anything. It's a little technique that I institute when I go through and do this, especially for bigger numbers like 72 or 140 or something. You don't want to miss anything. It's very easy to get a whole list of 5 or 6 pairs that work, but then miss that 7th one and you don't have the whole list. Okay, so here's a little way. First of all, what I like to do is I like to categorize it as a list of pairs, and I always start with the number 1, right? Because 1 times itself will always work, right? So I start there. Then on the left side, I add 1. I try the next natural number. In this case, the number 2. Well, 2 definitely divides 28. 28's even. We'll talk about divisibility rules in just a moment. Well, in another video. But 2 does go into 28, right? If you divide it out, you'll get 14. And so 2 times 14 is 28. So 2 and 14 are divisors. Let's try the next number, 3. Well, 3 won't work, right? 3 is not a divisor of 28. In fact, we would write that out as 3 is not a divisor of 28. Okay, we slash through the divisor symbol. Double check. Yeah, I did that the right way. Yeah, it's a forward slash. So 3 does not work. The number 4 does. Because 4 times 7 is 28. Then you just keep going down the list. Make sure we haven't missed anything, right? So the number 5, that doesn't work. 5 doesn't divide 28. 6 also does not divide 28. The remainder would be not 0. As soon as you hit a number, if you keep going down sequentially, as soon as you hit a number that is repeated on the other side, you actually know that you're done. 8 definitely won't work. 9 won't work. 10 won't work. Because at this point, if 8, 9, or 10, anything bigger than 7, if it worked, it would have worked over here, which would have had another number in between here, in between the 2 and the 4. And so we guarantee it didn't work because we didn't skip anything in there. Okay? So, well, I didn't write it down, but I skipped the 3, but we actually covered it. I just didn't write it down. So, so I know we have everything, right? I know I've covered all my bases. I didn't have to check all 28 numbers. I really only had to check up to 7 because I know once I repeat 1, I'm done. All right. Similar for 72. So I start off with, 72 is 1 times 72, and then I just go down the list, working through my natural numbers. So 1, 2, 3, 4, keep going, right? So 2 times, if you divide 72 by 2, you're going to get 36, right? 2 goes into 7 3 times. 3 times 2 is 6. Subtract, bring down the 2. 2 goes into 12 6 times with a remainder of 0. So get that remainder 0, that's 36 times. Okay, I could repeat the process. I won't do all the long division, but you could check me on these, make sure they work. I'll just save a little time and run through them all. 3 goes into 72 24 times. 4 goes into 72 18 times. Okay. 5 does not go into 72, right? 5 is not a divisor. 6 is. 6 divides 72 12 times. 6 times 12 is 72. 7 will not work. 8 will. 8 times 9. And then I try 9. Well, as soon as I hit 9, I have it repeated. And so I know I haven't missed anything because once I hit something on the other side, I know I've covered everything on the left, which means I would have had to cover everything on the right. So everything less than 9 is here, everything greater than 9 is here. Anything greater than 9 would have to pair up with something less than 9. So we know it can't. So at that point, we're all done. And this is the list of all the numbers that divide 72. Okay. What's interesting now is that every one of the numbers, let's actually look at 28 for a moment, because every one of the numbers that's a divisor of 28 is either prime or composite or 1, right? Those are the only three options we have anyway. Well, 1 can't be further divided. 2 can't, it's prime. 7 can't, it's prime. But if you look at 4, 14, and 28, those are all able to be divided further, right? They are composites, so they have their own divisors. And so you could, kind of go further with this, right? Multiplication can be, you can multiply multiple numbers, lots of numbers together. So let's say I look at 4 times 7 for a minute. Well, 4 I know is really 2 times 2. So think of that as 2 times 2 times 7, right? Let's look at the 2 times 14. Well, 14 I know is 2 times 7. 2 times 7 times 2. Interesting, it's the same combination, right? Up here I know 28 is, so this is 1 times 28, which is, we just showed that 28 is 2 times 2 times 7, right? And so what we really end up with is this unique factorization, and if we exclude the number 1 here, we have this unique factorization down to prime numbers, right? The prime numbers were 2 and 7. And there's only one combination of prime numbers that will multiply, or that will divide the original composite, right? In this case, it's 2 times 2 times 7. Or we could say 2 squared times 7, right? That's the exponential form. It's kind of simplified because we don't have to write out all the factors. All right, so 2 squared times 7 is what we call a prime factorization. It's a list of only prime numbers that factor 28, and it's enough of them to get all of 28, right? It's not just the 2 and the 7 to get 14, it's 2 times 2 times 7. 72 is very similar. However, if you look at all the prime numbers on this list, you got 2, you got 3. Is that it? Everything else is composite. Yeah, everything else is composite. Oh, except for 1, but 1 we don't do anyway. So 2 and 3. So 72 is just a long list of 2s and 3s. And what we'll end up with is a unique list of 2s and 3s. So if you think about it, if you break this down, and it gets kind of long to write it out, but there's a kind of a cool diagram that we often use called a tree diagram to help us to easier break these numbers down. I'll show you the tree diagram here on the 72. You start with 72 and you choose any combination you want of factors. Let's say 72 I knew right away is 8 times 9, right? And so I don't maybe recognize all these other ones, but I know it's 8 times 9. I'm familiar with that. Okay, maybe you are too. You pick one that you know. Well, 8 can be further broken down, has its own divisors of 2 and 4, right? And 2 is prime, so I'm done there. I could write 1 times 2, but why bother? The 4, however, can be further broken down, right? The 4 is 2 times 2. So we've got all primes down here. The number 9 is also composite. It can be broken down into 3 times 3. Okay. And so if I were to just grab all the prime numbers off of here, there's 3 2s and 2 3s, right? So it's 2 times 2 times 2 times 3 times 3. Or to write it more simply in exponent form, it's 2 cubed times 3 squared. Okay, that's what we call the prime factorization. So the prime factorization is where you break down a composite number into only prime factors. Let me go ahead and write that up here. So prime factorization is how would I actually define that? How did I just say that? It's breaking down a composite number into only its prime factors, right? Is factoring a composite number into its prime factors. Something like that, I don't know. Not the most technically precise definition. I'm sure there's a better one in the textbook here. Prime factorization, here we go. Expressing a composite number as a product of prime numbers. Okay. Expressing a composite as a product of primes. That is the prime factorization. Okay. So in our case, prime factorization here for 28 is 2 squared times 7. For 72, it's 2 cubed times 3 squared. Those are the prime factorizations. Okay. Yeah, I think that covers those. Oh, there was something else I want to mention. I knew there was something. So, what's interesting is with the factor trees, it's not unique. The design of the tree is not unique, but the end result is unique. So let's redo the 72. We could even do this 28. Actually, the 28 will be, doesn't matter. Let's do 72. So let's say instead of 8 and 9, let's say I knew it was 2 times 36. 36, well, I know 36 is 6 times 6, right? And I know that, of course, it's also 4 times 9, 2 times 12, or 2 times 18, but whatever. I know 6 times 6 pops off in my head very quickly. 6 is obviously 2 times 3, and this 6 is also 2 times 3. Well, notice I still have 2, 2, and 2, that's 3 2s, 3 and 3, that's 2 3s, okay? In fact, it won't matter the order in which I break these down. I could do 12 and 6 and keep breaking it down, but no matter what combination I have, I will always end up with the same prime factorization. So for any given composite number, the prime factorization is unique, all right? So that is a very, very important theorem. In fact, it is given a name called the fundamental theorem of arithmetic, okay? So I'm going to write that up here, the fundamental theorem of arithmetic. Actually, let's capitalize that F because this is a proper noun. The fundamental theorem of arithmetic basically says that the prime factorization for any composite number is unique. So it should be at the beginning of the sentence. The prime factorization for any composite number is unique. Okay, it's unique. That means there's only one of them. So no matter how you break it down to begin with, you'll always end up with the same combination of prime numbers in the end. Okay, now that can be proven. The proof is beyond the scope of what we're going to do here in this course. So anyway, fundamental theorem of arithmetic.